Yeah. So welcome once again. So this is Vlsi engineering class. So today is the lecture I have written. You can see it here. So today is the lecture one, but actually we had an one day lecture that is basically type of introduction, discuss the fundamentals and the basics about this Vlsi engineering course. Right. So as discussed in the last class, you know that the portion of this course would be regarding the digital IC design, right? So digital integrated circuit design. So digital integrated circuit basically consists of different gates. For example, NAND gate, AND gate, NOR gate, right? So NOT gate or the inverter, this is one of the most fundamental logic gate, right? Because you can have only one input and one output, right? And if you know how to design and what are the significance of this transistor level designs for MOS inverter, okay, or for say for any NOT gate, how do you want to implement, that is up to you, but mostly we will consider it in terms of MOSFET. So we are saying it as type of MOS inverter. Right. But if you know how to design one MOS inverter and what would be the implication of these different transistor parameters on the performance in terms of this digital IC, then you should be also able to apply the same concept for different other gates as well. For example, some complicated gate, may say 3 input and NAND gate, right? You should be also able to do that. So we will start our understanding or discussion from the MOS inverter itself, okay, and slowly build up our understanding as well as this discussion from starting from this MOS inverter towards this more complicated gates. Okay, we'll also see how the sequential circuits work and how to design those sequential circuits, but that will be later on. Okay, right. So when I say this MOS inverter, I think all of you are already familiar with MOS inverter. So MOS inverter is, let me write it, MOS inverter, right? So as in this is the most fundamental logic gate. So a couple of things I will also write here as discussed, right? Circuit symbol like this as shown here, right? This is the input, this is the output, right? Input, output, and if you want to see in terms of truth table, then when this input is at logic 0, output would be logic 1. When the input is at logic 1, output would be at logic 0. Now here, one thing you need to remember that, okay, that I will come maybe a bit later on. So in terms of then these characteristics, V output versus V input characteristics, okay, how these characteristics would look like for this particular gate. It's not even visible, right? Okay, let me try. How this would look like, okay, for this gate, if you want to plot this V output versus V input characteristics. It's simple, right? This is V output, V input characteristics. So from say like from starting from 0, okay, when the V input is equal to 0 to say up to VDD by 2, right? Say if it is a VDD is equal to 5 volt, then up to 2.5, you give any voltage, then the expected output is to be 5 volt only, VDD only, right? And if you apply any voltage beyond this beyond VDD by 2, that is in this region from VDD by 2 till VDD, then you are expected to get an output voltage which is equal to 0, which indicates the logic 0 level, right? So one thing from here, it is should be clear to you that when we are saying that input level, right, for this input level means this one, right, this inputs, this logic input logic 1 or logic 0, right? But we are defining this input in terms of some voltage levels, right? And see, the voltage level is not actually here quantized, but it is a type of range of voltage. See, for here we have defined that logic 0 would be for input voltage from 0 to VDD by 2, right? From 0 to VDD by 2, this is of logic 0 for input, and for this output, we have defined it is from this VDD till V in, right? So it is basically a range of voltages. It is not actually a quantized or particular voltage for the input side, right? But here, for this case, okay, we can see the output is either at VDD or the output should be at 0. But that is true. That is true for an ideal gate. Okay. But for practical gate, we will see that we will not get actually this type of characteristics, but we will get some characteristics which is bit different. Different in the sense, maybe with some characteristics, something like this. Okay, we will get some characteristics like this. So there we will also see that we have to define some voltage in terms of output. So where we have to say from like this voltage, this range of voltage, we have to say that this output voltage is at logic, this output voltage will represent logic 1. Similarly, we have to also define here some range of voltage where we have to say this is voltage or this output voltage or this range of output voltage is representing the logic 0 level, right? So for detailed IC design, so please be clear, make clear this point here only. It is basically a range of voltage. It is not a particular fixed voltage, not in terms of input, neither in terms of output, right? Okay. Now, this particular plot, what we have drawn here, this is V output versus V input characteristics. This is called the voltage transfer characteristics. Voltage transfer characteristics, or in short, it is called VTC. So please note this term, this VTC, that stands for voltage transfer characteristics, because in this particular course, we will be using this term again and again, voltage transfer characteristics, right? Even in the question paper, you might see some term written like that, VTC. So you should understand this VTC stands for voltage transfer characteristics. Basically, it is the output versus input characteristics. Sometimes it is also called as DC transfer characteristics. Fine. Okay. So I hope this part is clear. This is a very fundamental and very basic thing. You already know that, right? Right. So now, when talking about this MOS inverter, how do you make an inverter? Right? Suppose you have to make one inverter like this, right? How to make it? So the basic construction would be like if you want to implement it using this NMOS, then take one NMOS, take it here, right? Connect a load and then apply this VDD. And this is the basically the input side. This is here, you will take from the drain side, you will take the output, right? And that basically makes a very simple NMOS inverter, because you know that when this V input is low, right, then the V output, because this transistor would be off. When this transistor is off, then this V output would be equal to VDD. When this transistor turns on and this is completely on, then this V out will keep on falling, and when this V in is equal to VDD, then this V out will be significantly low or close to zero, but not equal to zero, right? Okay. Now, regarding this, I have a question. Please tell me, here I have shown this V out, right? So do you know that this would be connected with what in digital IC? Or what would be the load? Do you think that can we consider one resistive load here? Yeah, please tell me.
So we used capacitors earlier.
We used capacitor. We use capacitor means is there any reason why we use capacitor here? Your answer is correct, but just wanted to know.
Store charge.
Store charge, but why we have means use capacitor means what is the fundamental means why not resistance?
Sorry, it could store voltage which would help in providing the input to the next.
Right. Because when if you are designing one inverter, then it is expected after that the output of this inverter is also driving some another gate. Maybe it is another inverter, or maybe it is an input to an another, say, NAND gate, right? So these gates, when you consider this gate means the input of these gates, right? So what do you mean by input of this gate? See, input of this gate is basically the gate of the MOSFET, right? So what is this gate of this MOSFET? It is nothing but the major capacitance would be the gate capacitance, right? So it is basically the gate capacitance as of now. Later we will also see what are the other capacitance that will also come here. Okay, but as of now you can clearly see that it is basically we have connected it with the gate. So obviously the gate capacitance it is going to see. And one more thing is that as this output is connected to another digital IC, another digital gate, right? So definitely it is been connected with the gate terminal of next MOSFET. Okay, maybe let me draw it here. Okay, I will write this V out in the top, then it would be easier. See, we have another, say another inverter we have connected here. This is VDD. This is R, right? And here we have this output. Right. So definitely you can see why this capacitance is coming. This is not capacitance that we have connected means intentionally, but it is the capacitance of this next gate, right? That is coming due to the next gate, right? Now, one more here. If I ask, then what is the current that is flowing through this capacitor, means through this gate, right? Or this gate, as you know, this gate current of any MOSFET is ideally close to zero. So you can say that whatever current is flowing, okay, from here VDD, that current has to flow only through this, except the dynamic situation, means on the charging or discharging time. Other than that, if there is any DC current, that has to be flown through from this VDD to the ground only, right? It will not flow through this gate, right, through the MOSFET gate, right? Okay. So you understand why this capacitance would come here, right? This capacitance is also sometimes referred as the CL or the load capacitance. Okay. Now, here I have mentioned this load. Okay. Because here this you can replace with another means you can replace this load with an means you can consider load as an resistance to be as a resistive load inverter, right? Eventually you can connect one transistor here, or how to connect and all these things, if you know, fine. Otherwise we are going to discuss those things in much more detail, so we'll see there only. So as of now, let us say to a very simple case, so let us consider only this resistance only. Okay, so this our total circuit then turns out to be something like this, right? The second case, this circuit only. So you have this R, we have this MOSFET, and we have this, right? And to make the circuit complete, let us also put this capacitance, okay, which is coming due to the next gate, right? The gate after that, right? Okay. So here, see what is happening. Say this V out is equal to 0. Okay. Say this V out is equal to 0. Okay. Now, when this V out is equal to 0, you apply V in equal to 0 volt. Right? When you apply V in equal to 0 volt, this transistor is off, right? Current flows then, and this current now it will charge. It will charge what? It will charge this capacitor, right? And when this capacitor is fully charged, it will be charged up to what volt? Please tell me, it will charge up to what volt?
VDD.
Right. So it will charge up to VDD, right? So you can see through this resistance, this capacitor or this output node potential is rising from 0 to VDD. So it is pulling off the voltage at this output node. So that is the reason why this part of this circuit, see here it is only a resistor, so it is an element, but it can be a multiple couple of other things as well. Means not only one resistor, it may be a combination of 2-3 components as well, if you want, right? So this particular part is called the pull up network. You understand? This is the pull up network, because when this V in equal to 0, this current flows through this and it helps to charge off this output capacitance, means it will try to increase this potential, the potential of this node from 0 volt to VDD, right? Okay. Similarly, if you consider the other case, say here this V out initially is equal to, now it is fully charged, right? So it is now fully charged to VDD, right? Okay. Now it is fully charged to VDD. What we are doing? We are applying a voltage which is V in equal to VDD. So when this V in equal to VDD, so that means basically what you are doing? You have completely turned on this transistor, right? So this capacitor or the stored charge in this capacitor will now try to flow back to this ground, okay, through this MOSFET, right? So basically this capacitor get discharged through this MOSFET. As a result, the output potential, which is earlier VDD, now it will drop from VDD to 0 volt, right? So as a result, this particular part, right, is called the pull down network. So I hope this definition is clear to you, the what is pull up network and what is pull down network, right? So if this part is clear to you, then let us see, the go to the next case, and yeah, let us go to the next case and see what is this. So you are already familiar with the term VTC, voltage transfer characteristics. So we will take our discussion from now here only, this VTC, right, from the ideal VTC itself. Okay, and then see how does this ideal VTC deviates, means how does the practical VTC deviates from the ideal VTC and all this stuff. Okay, slowly we are building up our like foundations, right, so that we can discuss the couple of other things, means bit more complicated things based on that. So here let let us not right now jump to this real MOSFET, real NMOS transistor. Let us consider as of now the ideal case only. Say this ideal VTC only. So for ideal VTC, how does this would look like? Means how does the VTC would look like? This is the ideal VTC, right? So here you can see from 0 volt to VDD, the output voltage is at logic. Output voltage is at VDD, means the logic 1, and from VDD by 2 to VDD, output is at logic 0, that means 0 volt, right? So it is the ideal case. But if you now consider a real NMOS inverter, okay, which is this one only, then how does this VTC will change? So let us discuss that. But before going to that, let us also try to recap how do you get, means how do you make the VTC, okay, from this circuit only. Okay, so the basic thing which you already know, but this is type of a recap. So what you have to do, this is the transistor, you know the ID current is flowing through this, right? So ID current, so you have plotted ID, that is a drain current, right? And here we have plotted VDS. So what is VDS? This is drain to source, right? So this is VDS, right? And here you can see VDS is nothing but V out, right? So let us write that VDS is equal to V out. So it is, we are plotting then basically ID versus VDS, which is nothing but equal to V out, right? Now you already know MOSFET characteristics. MOSFET characteristics, what will be the characteristics of versus this what will be the output characteristics of a MOSFET, ID versus VDS? It would be something like this, right? So I have plotted the characteristics for different input voltages. So what are the input voltages? Input voltages are here V in. So I have changed this V in. So once it is below threshold voltage, then the characteristics is something like that, no current, right? Then I have increased this to V in 1, then V in 2, V in 3, then gradually the current increases. So that's how it forms. Say we have gone up to 5 volt. So 1, 2, 3, 4, 5 volt, right? And the characteristics look something like this, right? Then you can also write an KVL, okay, along this, KVL along this, which will give you nothing but this load line, right? So take a load line, means draw the load line here. So you know what is the voltage. I'm not writing it here. So please, okay. Now, can you tell me what is this voltage? Means what will be the this current value?
VDD by R.
Right. Okay. Right. So this is the load line, right? And the intersection of this uh, line, black lines, and this pink color line would give you the points, right? So here we have first this point, then this, then this, then this, right? So from say 0 volt to 5 volt, right? Then you can even increase if you want more data points. Then what you have to do, you can, instead of 1 volt, maybe you can plot at 0.6 volt, 0.7 volt, 0.9 volt. Then you will get much more intermediate point, right? Much more intermediate point of this, right? Much more intermediate. So you can do it. So what I am now talking about is the graphical illustration, means how graphically you can find it out. Obviously, analytically also you can do that, and we have to do it, right? So that we are not talking right now, because you know the equation of this, right? This line, you know the equation of this line, right? If it intersects here, you know the equation of this line. So two lines, you know the equation, so you should be able to find their intersection. So you can find analytically, no issue in that. But now we are for just type of for your visualization, I am now right now doing it in which way? Graphically. Okay. So here, if you have to plot now VTC, so VTC, then you have to plot basically V output versus V input, right? So what is V output? V output we have already seen is nothing but this VDS, right? So this is the voltage here. Here, this one will give us the points, which is V output. And V input is what? V input is here, this, how we have changed. Then I think it is quite clear from here. See, until and unless this V in is greater than the V threshold voltage of this MOSFET, so this MOSFET will be off, no current, right? So from that, you know that, right? Until and unless we are reaching this, say this VTHN, means the V threshold voltage of this NMOS, so current would be zero, and the output voltage would be constant at, please tell me, output voltage would be constant at
VDD.
VDD.
VDD only. Okay, so till VDN. After that, what will happen? After that, the transistor will turn on, and when the transistor will turn on, see, you can see after that, it will, as you are changing from here, it will move, means the output voltage is decreasing, right? So output voltage is keep on decreasing. So you can see output voltage is keep on decreasing. So output voltage will decrease, fall, and go here. Okay, and it cannot go any further, right? So it will again type of go and saturate, 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 saturate like that here. We will do this exercise in much more detail from analytical point of view. So maybe I could have done one thing here, which is not okay. Actually, this and this not that way correlated, because here, see, these points are like, as you are changing it gradually, it looks like it is falling type of linear way. But here what I have shown to illustrate it, because I need it in the next page, I need this type of diagram to illustrate that. Otherwise it would be confusing, for you. But for here, from here, if you really want to plot the VTC, then probably the correct drawing would look something like this. Okay, probably the correct drawing would be would look something like this, not this type of abrupt thing. Okay, but if you have understood this, because it's not like that you cannot get this type of characteristics from this resistive NMOS inverter. You can get it. You can get it. You have to choose this Kn value, means the transistor parameter, and the resistance value accordingly. So you will also get a characteristics, VTC characteristics, something like this, right? Don't worry on that. But the thing is that this, from this to this, yeah, it's not really matching. Maybe this would be a better VTC representation, which is coming out of this plot, right? Okay, so here I have one more question. What is this voltage? What is this voltage? Quickly tell me. Aniket?
So can you repeat which voltage you're asking about?
Yeah, this voltage.
So that's zero.
That's zero. Do you think that this line I have made some mistake? Should it be at zero, or should it be, or is it correct?
So no, sir, it should not
VDS
be
at
zero. PDS saturation.
Right, it cannot be zero, right? As you can see from this graphically as well, right? It can never reach to zero, right? Because you can see here, you have still this much voltage that has been dropped across the transistor, right? So it cannot zero. We cannot be equal to zero. So it is the VTC. Right? So in VTC, it does not mean that always this point has to be equal to VDD and this point has to be equal to zero. That means you should not think that this 2 voltage is the highest voltage of your supply rail and this is the lowest voltage of the rail. No, it's not like that. It can be any other voltage as well, right? Okay. So you have understood now how to get the VTC, right? From a simple this graphical method. Now let us take this VTC, okay, and go to the next page and see some of the important point in this VTC. Right. So this is VTC. That is what we have discussed. Do not consider this green line, green writing part and all these things. Just consider the blue axis and this black line, which is exactly similar to the previous one. Now I have removed one point from here. This is this VTN point, the threshold voltage part I have removed because it is no longer needed here. Because otherwise it will looks much more messier. So here, so this is the VTC. Okay. Now important points. So this point, right, as you can see here, this point, this is which is actually for this particular case is equal to VDD. We have termed this point as VOH dash. Remember, VOH dash, right? And the lowest point, the lowest voltage, output voltage, we have termed that value as VOL dash. Okay, please give me some time to discuss like what is this VOH dash and all this, why it is so important. Okay, so we'll understand that, right? But as of now, just try to understand like this is VOH dash and this is VOL dash. Hmm? Okay. Now you see when you are increasing this V in, this line falls and takes the shape, right? Okay. Now when it is falling, right? So here up to from here to here, it is almost parallel, right? Actually, it is parallel. But after that, it will fall. So when it falls, that means it should gradually increase its slope. So slope is increasing. So here, this particular point where the slope becomes equal to -1, where the slope becomes equal to -1, that particular point we have noted. Okay, so I have written it here, right? dv out by dv in is equal to -1 for this point, right? So this is exactly at -1 here. Now, if you keep on increase this V in, the slope will further increase, right? And it is increasing, right? Slope is now much more, means the mod of slope is now greater than 1, right? Right. Then here, you can see here, again, the slope has started slowing down, right? So when the slope has started slowing down, then obviously at some point, it will again reach to -1, the same value. So we have noted that point as well. So we have noted these 2 points here, where the slope is exactly equal to -1. Right, after that the slope will become less than means it will be mod of slope is less than 1, right? And it will become something like this, right? Now these 2 points where the slope become equal to -1, we call this point the higher, this point, okay, on the above, or you can say the top level, higher output voltage level, we call it as VOH. Okay, so this is VOH, and the lower one, the in the output side, it's called this VOL. Okay, and the corresponding input voltage, we have termed them as follows. This point is as VIL and this point as VIH. Okay, right? So VOL output, corresponding input VIL, VOL output, corresponding input VIH. I hope now this means we will not make any mistake in identifying these points. Okay. Now, what is this VOH? Now, let us discuss this each and every point one by one. What is this
Sir,
VOH? Bolo.
so what is VIL?
What is VIL? Okay, so VIL is the point. As of now, we are defining in terms of point where uh, VIL is the input voltage, right? For which the slope of this VTC would be equal to -1.
Okay, okay, sir.
Okay, okay. So, what is VOH? So, as you can see from here, this VOH. When we are discussing this VTC, we will say anything above this VOH, we will consider that voltage to be as output 1. So, anything above this VOH, we will consider it to be as logic 1 in output. What is VOL? VOL is the voltage level in the output side. This is the maximum voltage level in the output side. That means below VOL, any voltage in the output side would be considered as logic 0. Okay. Okay. So as I have mentioned to you, this VOH for this particular case means for this case, this is equal to VDD, but it is not the generalized one, right? So it might be that it is not equal to VDD. So that in that case, VOH dash is not equal to VDD, and you can have some range of voltage in this output side starting from VOH to that VDD level, which is considered as logic 1 output. Similarly, any voltage in the output below VOL is considered as logic 0 output. Is this two definition clear, or do you have any doubt in this? Clear, right? Okay. Then we can see what about this VIL and VIH. So VIL is the maximum input voltage, okay, that to be interpreted as logic 0 in the input. So VIL is the input voltage. This is the maximum input voltage that can be interpreted as logic 0. So that means any voltage from 0 in the input side to VIL is considered as logic 0. Then I think VIH definition is also automatically been clear from this. So VIH is the minimum voltage in the input side which can be interpreted as logic 1 in the input. So that means any voltage from VIH till this VDD can be considered as logic 1, right? So one thing is quite clear from this, that this VOH, VOL, VIL, VIH, okay, these are dependent, okay, on the VTC of VTC of this gate only, right? If this VTC changes, means you change the design, as a result your VTC changes. Your VTC changes, these values will also change, right? So that way, the minimum definition of this, or the values of this, rather than the values of this minimum input voltage for to be considered as logic 1 or logic 0, no, not minimum voltage for logic 1 and maximum voltage for logic 0, that also changes, right? As you are changing the VTC, means as you are changing your design, right? So is this definition clear to you, this four, or you have any doubt?
So is there any reason for considering the slope as -1 as the limit? Like why not -2?
Okay, okay. So why not -2? That is because okay, maybe that would be better if we consider it to be here, okay, in the regenerative part. So here -1 is something like this. See, right, if Okay, maybe okay, put it in this way. So what is the slope, maximum slope from here to here? Please tell me, what is the maximum slope from here to here? Yeah, you have asked one question, right?
So the slope can be from 0 to -1.
0 to -1. Okay, so 0 to -1. That means if I say mod of slope, then the mod of slope is less than 1, right? Okay, so any change, okay, if you now put any change in this input, right? So VTC is what? VTC is basically this output versus output versus input, right? So say this is that function, this function, right? So V output, this is basically the slope, mod of slope versus V in. So any change in this input side, maybe suppose maybe some due to noise, okay, if the slope is less than 1, that will be reflected less, okay, in the output side, right? But if you are crossing this point, then that would get amplified, right? Means any noise, if it is coming within this range, that would be reduced. Is that gives some idea like why you are choosing -1 to be the limit?
Yes, sir.
Okay, great.
Sir,
So,
so what is the logic for the input voltages between VIL and VIH? What logic do we consider for those input voltages?
VIL and VIH means I think I have said like voltage from here to here to be considered as logic 0, and voltage from here till here is to be considered as logic 1.
No, sir, in between VIL and VIH for those
Oh,
range
for
of.
why we are not choosing? Okay, here we are, this is called type of, again, type of, forbidden region. We do not want to operate the transistor, the gate particularly in this region. This is a very high gain region, right? In digital, we do not want really that gain, that part. That is for the analog part. Okay, this is for the analog domain. So we do not try to come to this region for our, steady state or for some stable output design. Okay, so this we really do not want to operate. Okay, so here, if these four things, four terms, or the definition of this four term is clear to you, then probably you can also understand this thing very quickly. See, this is very easy. Say one inverter is driving another inverter. So you have termed them as inverter 1 and inverter 2. This is inverter 1, this is inverter 2, right? And let us focus only here. Let us not focus at this input side. Okay, only at this output side. Output of first inverter. So output of first inverter, it might be what? It might be anything, right? Depending on the input voltage or depending on this construction of this inverter, it might be anything between VOH to VDD, right? That's how we have defined, right? This, or we will design that this output voltage, if this output voltage is at logic 1, if this output voltage is to be at logic 1, then this output voltage has to be within VOH to VDD, right? Okay. Similarly, if this output voltage has to be logic 0, then this voltage would be between 0 to VOL only, right? That's how we have defined. Okay. So this is the then range, right? Depending on this design, depending on the input at this, so input is what? This input definitely we will logic 0 or logic 1, right? Depending on we will get here either logic 1 or logic 0, right? So here we can see we are getting a type of band, right? So this is the band that is allowed at this output. That's again I have talked here, all right? Same thing we are trying to say from here. So you have a band from this, which is a valid output of this inverter. Similarly, you have a band of voltage, which is a valid logic 0 output for this inverter. Now let us shift our focus from this inverter to this inverter. Okay. So if we shift our focus from this inverter to this inverter, right, and obviously it's input side, then how we have defined this input? We have defined that the input, okay, if the input is at logic 1, if the input is logic 1, then the maximum input can be VDD, maximum voltage can be VDD, and the minimum one would be VIH, right? And so definitely we can say that it is from this VIH till VDD. So it is from VIH till VDD. Or if it is logic 0, then it can be from 0 to VIL. That is also we have seen from here. If it is logic 0 for this input side, then it is from 0 to VIL. So we get a band of this input side like this. Right? This is for logic 0, this is for logic 1 input, right? So, and you also noticed probably one thing, that we have plotted this y-axis. I do not know what is the x-axis really here, but the y-axis is definitely voltage, right? So y-axis is voltage, and see, they have the common axis, right? So starting 0 from here and VDD here, right? So that's how we have put them side by side, right? Now you noticed one thing which is very important. Say between this, okay, and you have suppose this channel is quite long, means this wire is quite long, and there is a possibility that noise might come in, right? This noise might come in here. There is a possibility between the between this output and to this input, noise might come in. So if due to noise, if this output is getting perturbed or disturbed, then what might be the case? Then see, okay, now consider this output was initially at logic 1. So if the output is initially logic 1, that means it might be anything between this value to this value, right? Now if this logic 1 has to be has to be passed to the next gate, right? Means if the logic 1 has to be come to the input of this gate, then any voltage between VIH to VDD would be sufficient, right? Means this is the valid input voltage for this second gate to be considered at for this gate to be considered as logic 1 input, right? So that means you have this much region of voltage where this noise can be introduced, and noise can change this level of voltage. Say the level was VOH, now noise can change this VOH level to here, say from here, but still it is within the valid range of input voltage for this, right? Say the noise is a little bit more, it has changed this level to from here to here, still this in the this valid range. But if this noise is coming little bit more, say crossed here, then probably we come into this region where we do not want to operate the transistor, means to operate the particular gate, right? So this particular level, or this difference between this voltage level, is called the noise margin high level. It is represented as NM, means noise margin H for high, because it is for logic 1. So noise margin high. So this is the difference. So on the same token and same analogy, we can also say, if instead of this output was 1, say the output was 0 earlier. So if the output was 0, then the valid range of this output is to be this much. Say the output is for any, say the output is maximum only, say this level only. But still we have this much room by which the noise can change this voltage level, but still that can be treated as logic 0 by this next gate. Right? So this is the margin, right, by which noise can perturb the signal, but still that will not disturb the this operation of these two gates, right? So this particular margin is called the noise margin low, NML, and it is basically the difference between these two, VIL and VOL. So here I have written it explicitly. So you can see this is noise margin NM, noise margin high is the difference between these two, noise margin low is the difference between this and this. So it is obvious then, for any digital design, you would expect, or you would try to design to make the noise margin as high as possible. But at the same time, you should also have to notice one thing. Say for any design, say VDD equal to 5 volt. Okay, VDD equal to say 5 volt, and say VOH dash that is equal to also 5 volt, VOL dash that is equal to. I hope you are means you are able to now correlate to what with these terms. Okay, in this particular diagram. So VOH is this one, VOL dash is this one, right? And say from here we have calculated noise margin high, and that suppose comes out to be 1 volt, which is good. But suppose you have designed your design is such that the noise margin low is only 0.2 volts. That is not intended or not expected, because see, for the noise margin high side, you have kept sufficient margin. You have kept sufficient margin of 1 volt. Whereas for the noise margin low, you have kept only 0.2 volt as a margin. So while you are designing any digital gate, it is expected the noise margin would be high, and at the same time noise margin would be also symmetrical. Symmetrical in the sense means similar. Okay, if it is 1 volt, then that would be also around 1 volt. Okay, please let me know if you have any question down here.
So
Sir,
what would
so
happen for some?
Huh. Yes.
So what would happen for a pair of inverters if VOH is less than VIH? VOH of
V
first
okay.
one is
VOH means you are saying noise margin becomes negative.
yes, sir.
Yeah, noise margin negative, then then definitely it will cause something else. So that probably we'll see it here in next page. Okay, that is something. But okay, and one more thing, that is, yeah, you mentioned this. Then this noise margin should be greater than 0 if we define noise margin like this. Okay, yeah, I think someone else also have asked some question earlier.
yes, sir. So is you are saying like there is no application in which we require noise margin high to be greater than noise margin low or something like that. Like you are saying they're always
No,
equal.
no, 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 no.
We
I am
want
saying
them to be
no, no,
equal, or they.
no, 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 Harsh, what I'm saying, the noise margin, if you define noise margin like this, then the noise margin, that value should come to be positive number. Huh? And noise margin expected to be high.
Yeah, sir, that part I got, but the example in which you showed that noise margin high is 1 volt and noise margin low is 0.2 volt, you said
Point.
we usually don't require this. We are not able to get this, or like we don't require this. Are the
No, no,
noise
no,
margin
no,
high and low
no, no.
always equal?
No, no. See, the thing is that you can change your design. For suppose, let us focus again on this NMOS inverter only. You can change the value of this, this R value, and here this W by L ratio. By changing these two, you can actually modulate, these two value. So you have to make an adjustment, that like this is not a probably a good design. So let me change these two value and try to make these two as close as possible. Means try to make them large at the same time as close as possible. That is
Yes,
for a
sir.
good design.
Yes, sir. So I'm asking like, is there any application in which we don't require them to be close? Like, and one of them is very large and one of them is very low. Are there any such applications?
Yeah, that you have to like see if, for example, say for some of your design, say the output is for the most of the time is expected to be at logic 1 only. Okay,
Yeah,
so
exactly.
probably in that case you can think of.
Okay.
Sir, is noise margin high positive or negative?
Noise margin high, as we have defined from here, it is VOH value which is higher than VIL, so it is obviously it will be positive.
Okay.
Okay, so if this part is clear, then let us see this last topic for today's class, which is called the regenerative property of inverter. Okay, instead of 2 inverter, let us say we have now 3 inverters. Okay, so this V naught, this 1, 2, 3. And here the input was V naught, right? Okay. And say we do not know how this inverter was made, right? As of now. So we are assuming that the VTC of the inverter would be something like this. So this is the output, this is the input, output voltage versus input voltage, and the inverter is this VTC is something like this, right? Okay, I think I missed one point in the last page. So let me tell you that and then come back here. Okay, which is important. So here, yeah, no, not here. Here. So there is one more very important point that is called this VT. So you know what is this VT stands for? This is interesting. See, this VT stands for threshold voltage. Now you might say threshold voltage in the last page. We have said this is the threshold voltage, right? Yeah, that is true. This is the threshold voltage. This is the threshold voltage for NMOS, right? Actually, it is not that we call threshold voltage, but yeah, it's better to say threshold, threshold level. Threshold, okay, of this inverter. So that means ideally, if any voltage which is below this threshold voltage, if you give anything below this for this as an input, then you are expected to get a output which is logic 1, right? Again, I am repeating, this is the threshold voltage or threshold for this inverter, or threshold can be defined for any logic gate actually, right? If any input, if you have given below this threshold, right, then for this inverter, then you are expected to get a logic high output. If any input, if you have given beyond this VT, then you are expected to get a logic 0 output. That's how the threshold voltage is, a threshold is been defined for any digital logic gate. Okay, now how to get that threshold from this VTC? Okay, very easy. Draw the VTC, then plot a line. Okay, with which represents V in equal to V out. So that means just make a 45-degree line here, and the intersect of this line will give you the threshold of this inverter. So I hope the threshold concept is also clear to you, which I think I have missed while we were discussing this. And remember, this is not the threshold of the transistor. This is the threshold of as a gate, right? Okay. So let us come back to this. So we have 3 inverters connected in series, and the first input is V naught, right? And as mentioned, let us say that these 3 inverters are identical. So if they're identical, their VTC is also expected to be identical. Okay. And say the VTC is something like this. Okay. Something like this. The blue one. As I have written that function, I represented that function using f of x, right? Okay. Now, what will be the VTC of this gate number 2? Same. It will be same. What will be for gate 3? Same. No change, right? Because they are identical. But see, this is the input, right? So for gate 1, I have written this is the input, this is the output, right? So I can draw it like this. But what about for gate 2? So the output of gate 1 is now connected with the input of gate 2, right? So that means for this inverter, right, this would be the output, means this would be the output, and this would be the input. Just think, and if you plot it, you will get a curve like this, which I have
Sir,
drawn using inverted inverted f of x. Yes, please.
sir, sir, after this, can you please continue tomorrow? Because, sir, like the time is up and we also have labs and such things from 2 o'clock.
Okay, can you give me just 2-3 minutes more? Yeah, thank you. So, yeah. Um, so is it clear to you that if it is f of x, then for this gate, for the second gate, if I want to draw the VTC on the same plot, then that VTC would look something like this. Please let me know quickly.
Yes, sir.
Yes, sir.
So can
It
you
will be,
repeat
right?
for the second VTC? Are the axis like the other axis the same, or are we changing it up?
No, we are not changing it up. We are not changing it up. Right.
So then for the second one, the input is the input to the second one only, not V0, right? Like not at the first, not the initial input, right?
No, for the second one, the input is V1.
Okay.
It is the output of the first one, isn't it?
Okay, so understood.
You understood, right? See, you can, that's what I said, right? For the second case, this is basically the output and this is basically the input. Now you see, this is output, this is input, right? So this output is low. So you consider from here, this is the threshold, right? For the second gate. So this is the threshold. So below this threshold, right? You apply, that means this is at logic 0 input. So logic 0 input, so this is the output, right? For the second gate. So what you are getting? Logic 1 output, right? Again, if you go to the see the this part, so here the input is logic 1, but as a result what you are getting, you are getting logic 0 as output, right? So it is basically the this plot only. Okay, I think it is already 1:03, so I've crossed. So maybe it will take not 2-3 minutes, but maybe 5 minutes at least. Okay, so you understood this part, fine. So we will continue our discussion in tomorrow's class from this point only, huh? Okay, then thank you very much, and I will see you tomorrow.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Yeah, you are welcome.